So let's talk more specifically now about evaporative cooling. This is from the strategy called downdraft evaporative cooling towers. And this example is called the Laredo Demonstration Blueprint Farm. It's by Pliny Fisk. It's in Texas. And it uses a combination, again here, paired of downdraft evaporative cooling combined with uplift stack ventilation outlet towers. So let's talk about the evaporative cooling for just a second. You can see there's this kind of top or head on the evaporative cooling tower. That's the downdraft part. So this would have a kind of sponge-like medium. Could be rock wool or a kind of vegetable fiber or some kind of a synthetic fiber. Anyhow, it's a mat that's full of moisture. There's a little pump that trickles the moisture down through this sponge-like material. It's also permeable to air, so the air can move through it. As the air moves through it, it picks up moisture. As it picks up that moisture, it becomes more humid, so the moisture is added to the air. And at the same time, what's happening is the dry bulb temperature is dropping. So the humidity goes up, the absolute humidity goes up, and the dry bulb temperature goes down. When that cool, moist air, now it begins to be heavier, and the heavier air begins to fall. So it's creating a downward pressure. At the top of the system, then there would be a negative pressure, so it's helping to pull more air in. And then it goes down, and in this case, two of these kind of shed-like modules in this demonstration farm are linked. So it would go through the door into the other module, and then as it's doing this, it's picking up heat. So all of the heat gains from the building are being picked up by this cool, moist air, and it's beginning to warm up. As it warms up, as it's moving into the other side, then it begins to rise up again and out through the stack outlet. So just like FOTI, there's a kind of downward pressure and an uplift from the stack vent. So the nice thing about evaporative cooling is that it works especially in a dry climate. So it's not so great in a humid climate because you're already humid. So adding more moisture to humid air does not necessarily make it more comfortable unless you're in a really high heat gain situation. So in a hot, humid climate, we almost don't see evaporative cooling except sometimes in restaurant kitchens, sometimes in clothes washing or dry cleaning facilities, things that create a lot of internal heat gains, where being moderately warm and moist is still much more comfortable than being very moist and very hot. But most of the time we see it in a hot arid climate, so you'll see evaporative coolers all across the Southwest in their mechanical form and increasingly so in this passive downdraft form. The nice thing about the passive downdraft form is, number one, it doesn't use a fan to drive the air through the building, and number two, it gives the architect a nice opportunity to work with a vertical form. The evaporative cooling is also going to work when it's too hot outside to ventilate. So it could be 100 degrees outside, 105 degrees, and by cooling off the air through evaporative cooling, you can bring it back down into the comfort zone. You can also use it in a kind of indoor or indoor-outdoor situation, either one. So here's an example by Moule and Polyzoides at a courtyard for residential housing at the University of Arizona. And so the downdraft tower that you see on the left is actually cooling this courtyard space. And there's a kind of view of the courtyard on the right. So one of the kind of distinguishing factors with evaporative cooling is that unlike air conditioning, which recirculates the air, and you're trying to minimize how much fresh air you bring in and just bring in the minimum to, clear out pollutants and have things smell fresh and provide oxygen, right? In a evaporative cooling situation, it's more of a once through airflow. So using a little bit of water in the process, but you can have a much more kind of liberal relationship between inside and outside. And the outlets then become the windows and doors. So you just kind of crack the windows where you want the air to flow, and that's how it moves. Here's a project that combines a bunch of different passive cooling strategies. This is Grimshaw's UK Pavilion at the '92 Seville Expo. So it's a temporary structure. but it's using all kinds of interesting strategies. So in the upper images, left and right, you can see the water wall. That water wall is kind of a sheet of glass with water flowing down across it into a pool at the bottom. So it's doing a number of things. One is it's creating a kind of more humid, evaporatively cooled exterior. When it falls down into that pool, that's where people are queuing up in line. So you're kind of queuing up in line under the shade of trees with misters next to a pool in an evaporatively cooled environment. Once you get inside, there's a ramp that goes up next to that wall, and that evaporative cooling is now causing that big glass wall, instead of being hot, to be cool. It's facing east. Up on top, you can see there's a series of photovoltaics. Those photovoltaics are kind of sculpted and form a shading layer all across the top of the building. On the south end of the building, it's got a series of sails. So again, it's shaded by a kind of fabric sail-like structure. On the west side, there are water tanks or water containers that are filled with water and essentially become thermal mass and absorb and store the heat, so that the heat gain from the west is diminished and delayed until evening. And then on the left hand side at the bottom, you can see that the building is actually organized as a series of thermal zones. So take a look at the cooling zones strategy in sun, wind, and light. So this is the idea that not every part of the building has to be cooled to the same level. So the coolest part of this structure is the interior exhibit space, where people are inside of contained spaces like an auditorium or an exhibit room. And then it can be warmer on the outside. It could be warmer in the places that have less density of heat gain and less density of people, and where you're sort of moving around and on the way to something. So several different kinds of degrees of cooling treatment happening here. All right, now we move on to what's probably my favorite passive cooling strategy. This is called night cooled mass. So imagine that natural ventilation, in order for it to work really well, it has to be cooler outside than inside. So if it's hotter outside than it is inside, and you open the windows, you let the outside air in, what's going to happen? Well, the building is going to start warming up, not cooling down. So whenever it's hotter outside than inside, you'd rather have the building be thermally closed. That is, have the doors and windows, the envelope closed, and not let the outside air come in. So in many climates, what that means is that beyond about 80, 85 degrees, depending on what your tolerance is, you want to close the building. So there's a lot of time above 80 degrees, let's say in Knoxville, Tennessee, or Phoenix, Arizona. So there's plenty of months, or at least days or weeks or times of the day, when open natural ventilation is not going to be a benefit. It's too hot to ventilate, we say. So the solution for that, or one of the solutions for that, is night cooled mass. So night cooled mass is a kind of hybrid strategy of being open and being closed. When it's too hot to ventilate, we close the building. So sometime in the morning in the summer, it gets up above 80 degrees, and we have the building closed. Now, during the daytime especially, and especially when the building's occupied, you have lights, you have people, you have equipment. All these are producing internal gains. You have solar gain coming through the windows. That's usually a big one. And you have some conduction gain coming because it's hotter outside than it is inside. So all these are contributing to the building's rate of heat gain. When the building is closed, you have to do something with that heat gain. If you're not going to air condition it, then what we do with it in this case is store it in the mass. So the mass begins to then absorb those heat gains hour by hour across the day. The mass then has to be big enough to store that daily rate of heat gain. Then when the outside temperature gets cool enough, and we usually define that by it's cooler than the top of the comfort zone, or it's cooler than the mass temperature, then we're going to open the building. Typically that's going to be about 10 o'clock at night, and say in a climate like Knoxville, or maybe midnight in a climate like Albuquerque, where it's hotter during the day. It's going to take that long for the outside temperature to get cool enough. Then we ventilate at a relatively high rate of airflow for however many hours we have available to us when the air is cool. That cools down the mass. So ideally we enter the building in the morning and the building is cool and the mass temperature is somewhere near the bottom of the comfort zone. Then we close the building, and across the day the mass temperature begins to rise and the air temperature in the building begins to rise, so that we move up through the comfort zone and we end up somewhere in the middle or near the top of the comfort zone. This is a building in Oregon. It's a public utilities district building. You can find more about this in the book Mechanical and Electrical Equipment for Buildings. It's a night-cooled mass building that, even though air conditioning was installed, never got to be used. Now you'd think, well, the Pacific Northwest is a mild climate, and that's true, but it is an office building with pretty high levels of lights, people, and equipment. It's a daylighted building, which brings down the rates of internal gain, and it's got some significant south shading, so it's also looking at all kinds of ways to reduce the rates of heat gain. In any kind of passively cooled building, that's really what we want to do. First, we want to address the loads, bring the cooling loads down as far as we can, and then see if we can use the relatively weak forces of passive design to help to meet those loads. So in this case, we're using a hybrid system. It's not completely passive. It's using the mechanical system to distribute air. It's taking in outside air at night in an oversized duct system, dumping that air into the space. The air then moves around inside the space where it can contact any exposed mass surfaces. In this case, the ceiling mass is exposed and the vertical wall structural mass is exposed. So that can be cooled down. Then it's sort of sucked up into an intake through a kind of U-shaped precast concrete channel. The air moves up through that channel and then goes left and right horizontally through hollow core concrete planks. After traveling through the planks, then the air moves into another concrete channel and returns up and is picked up through the return duct system of the mechanical. So this at nighttime, this would be a one-screw system. In the daytime, the air would simply be circulated around through the system as necessary. So this is kind of an interesting and unique system in that it gives more exposed surface area because it's using both the bottom of the roof system and the internal cores of those hollow core planks. It's using both sides of the vertical concrete structure, these vertical bearing walls, and it's also using the inside of the concrete channels and the outside of those channels that's exposed to the room air. On the right, you see a north side view with a kind of T-shaped alto type window where daylighting is biased at the top and view is biased in the lower portion of the windows. Here's a section. You can see more shading on the right hand side. That'd be the south elevation with both louvers and then vines grow on those seasonally. Light shelves on both sides and then a cross section through that large mechanical duct in the middle. Then on the right you can see that duct system from below. In the night cooled mass strategy, you can find this map. It helps to find the zones where the potential for night cooled mass is good. So for example, Knoxville, Tennessee is in zone 5. In zone 5, in a skin load dominated building, night ventilation is possible typically from about May to September. And then from October to April, typically we would not use cooling at all. In an internal loaded building, it might be possible in all months in zone 5. And it would be too hot for night ventilation hardly ever, right? So zone 5 is pretty good for night cooled mass, although you have to look at the details of your particular place in your climate zone. So there's certainly days and sometimes weeks in Knoxville when it would be too hot for night cooling, or basically what would happen is that the nighttime temperature wouldn't go down low enough. Here's the sizing tool for night cooled mass. Now this is maybe one of the more complicated tools in the book, but we can break it down, and in the end it's not so complicated. So where we start with this is what we call the mass delta T. That is the temperature differential that's possible in the mass from its lowest temperature to its highest temperature across a 24-hour cycle. And that's defined as the interior temperature, which we take as here as 80 degrees is the top of the comfort zone. Now you could use a different number other than 80 if you want, but in most cases I like to use 80 as a conservative place, particularly in a high mass building. So 80 minus T-min plus 5 degrees Fahrenheit. So T-min being the low outside temperature during the day or the month that you're trying to evaluate. So once we know the mass delta T, let's take this example at 22 degrees. Then we move up vertically to the kind of thermal mass that we're using. That is the material that we're using. So just like when we're looking at heating mass, we'll see that materials with low density can store less heat than materials with high density. So sand stores less heat than adobe or brick, which stores less heat than limestone or concrete. So let's move up in this example. We'll look at an 8-inch grouted block, or that's about the same amount of heat storage as 4 inches of brick. From that intersection then, we move horizontally. And we'll move horizontally over to a ratio of mass area to floor area. Now, if we don't know this, we can take a guess at it. If we've already designed the building, then we can evaluate the proposal that we've put forward. In this example, it's using 200, which is 200%, which means 2 times as much mass area as floor area. So let's say you had a building with lightweight walls, but you had a concrete floor and a concrete ceiling. That would be twice as much mass area as floor area. From that intersection, then we drop down and we can read on the horizontal scale the mass storage capacity in BTUs per day per square foot of floor area. So this represents how much heat can be stored on a daily basis in that much mass. Now, we may not know the amount of mass, so we can also work this same chart from both directions. So we're going to know the mass delta T. That's a function of the climate and our interior set points. We're going to know the materials. That's our choice, right? But we may not know how much we need. So if we want to solve for how much mass we need, then we first go over and find the rate of daily heat gain that needs to be stored in the mass. We can find that out in the SWL tools. We'll look at in this case, the daily heat stored. This, as you can see here, we're taking a look at the quick heat gain page. We can also look at this on the detailed heat gain. So if we know the total heat storage that's necessary on a daily basis, we can start there on the bottom axis and simultaneously over on the left-hand side with the mass delta T, and we'll intersect both of these two pathways to find a required amount of mass. Here's an example of another high mass, night-cooled mass building. This is the Eastgate building. It's a combination of offices and shopping mall in Harare, Zimbabwe. The upper levels of this building are entirely non-air conditioned and entirely passively cooled. It's what I'd call a super high mass building. It's got a lot of mass both in the exterior and in the interior. It's a slightly hybrid condition. That is, there are supply fans that are taking in air through this shaded arcade. This would be a kind of multi-story shopping arcade down the center of the building. And then those fans are moving air horizontally through a mechanical floor, a kind of sort of half floor, as you can see. And then that's moving up in a kind of complex pattern through vertical channels, then horizontally through a hypocaust floor. Then it moves up through the space, out through the sort of center area of the wall, and then up through a stacked ventilation outlet. And you can see that on one side the supply gets smaller, on the other side the outlet gets larger as it moves up through the building. There's a detailed section on the upper left of how that air arrives in a kind of vertical way, transitions horizontally through a hollow floor, comes into the room at the edge, then moves kind of diagonally up and out through the upper interior, and then over into that central stack and up and out through a chimney at the top of the building. At the lower right, you see a kind of cross section of a termite mound, and the termites actually use a kind of similar system of channels and tunnels for stack ventilating the inside of the termite mound. If you can imagine all of that little termite activity with all of that heat being generated by the bodies of the termites, and the sun pounding on the outside of it, they actually need to have a passive cooling system. On the right hand side, you can see the interior of this Eastgate building. And then just to wrap up, so we've looked at cross ventilation, wind catchers, stack ventilation, night cooled mass, a series of different passive cooling strategies. There are a series of other strategies that can be found in sun, wind, and light, as you can see across the top axis of this chart. This is a chart called Climate Criteria for Cooling Strategies. It comes from the bundle spread in Sun, Wind, and Light printed volume. This allows you to look at some of the sort of pluses and minuses or characteristics of different systems and kind of how to evaluate them, which analysis techniques to use. You can see that there's a series of other strategies: roof ponds, mechanical space ventilation, and so forth, heat exchangers, other things that we haven't looked at in this presentation, but that you can also compare using that bundle. One of the things that the bundles are intended for, things like the passive cooled building bundle and the passive solar building bundle, are to look at the choices that you have. There's a bunch of different strategies, a bunch of different systems that are possible. And so the bundle strategies help you to look at and to compare and to try to begin to select which strategies might work best for your building. So I don't want to go into the details here of this, all the details of this chart. There's a lot to go into here, but you can study that for yourself in the bundle strategies. All right, so that's it for a quick introduction to the basic passive cooling systems. I hope you've enjoyed it, and thanks for solving the climate crisis by design.